Okay, we are in lesson 5 for our bonding unit. We're going to finish up with the other two types of bonding, ionic and metallic. Make sure by the end of this lesson that you can write the formula unit of a simple ionic compound. That means I'll give you 2 atoms and you're going to tell me what their formula unit looks like. No table 8.4. These are the characteristics of ionic and covalent. That reflects back on our last couple of lessons. And then recall that the unique properties of metals exist due to this sea of electrons. Know those things and you will do well on your quiz. Okay, we've just finished up covalent bonds, and covalently bonded things are called molecules usually. Ionic compounds, however, are composed of positive and negative ions. Remember cations and anions. And please remember, this is very important, this note right here. Although they are composed of charged ions, the ionic compound itself is electrically neutral. Okay, we have talked about this multiple times, but I want to make sure that you always keep that in mind. It's going to be very important in figuring out how they are going to bond. Let's take a look at how this applies in ionic compounds. So, when discussing ionic compounds and showing their structure using electron dot notation, we usually consider the changes that take place in ionic bonding in reference to the formula unit. Now, I have written the definition already for you on this, but it is the simplest collection of atoms from which an ionic compound's formula can be established. Here's an example right here, table salt. Its one formula unit is sodium chloride, which is 1 sodium cation, Na+1, and 1 chlorine anion, Cl-1. Now remember, sodium is in column 1 on the periodic table. That's why it likes to make a positive 1 charge. It wants to get rid of that 1 electron. And chlorine is in column 17, meaning it has 7 valence electrons. It just wants to gain that 1 electron so it can have a negative 1 charge. Example 2, we've got calcium fluoride. It is 1 calcium cation. Remember, calcium is in column 2. That's why it wants to be a positive 2. It wants to get rid of those 2 valence electrons. And 2 fluorine anions. Fluorine is in column 17, just like chlorine. Therefore, it wants to gain 1 more so it can have the full octet of electrons. So again, remember, ionic compounds themselves, let me get my pen back on. Ionic compounds themselves are neutral. So, are neutral. So this is, so what? So, cation and anion charges have to balance. That's why in example 2 above, right here with the calcium fluoride, that's why you'll notice there have to be 2 fluorine anions to balance out and make sure that the final compound itself is neutral. And that looks like this. We can figure out this formula right here by just talking through what happens to them. If you'll remember, metallic atoms, they hold some of their electrons rather loosely. Remember, calcium has 2 valence electrons. It holds on to those really loosely because it has much lower potential energy, and it's much happier when it gets rid of those. Bye-bye. They're going away. So that it can have an octet. And when that happens, it loses those 2 electrons, so it becomes more positive, or this. Fluorine is a nonmetal, and it has 7 valence electrons. Okay, and so therefore it tends to find electrons and grab one. That way it has its octet as well. As it grabs onto one electron, it becomes a -1 charge. You'll see this either way. So it's pretty easy to see that if you want to balance out the larger charge of +2, you've got to have a -1 and another -1. Okay, that adds up obviously to -2, and +2 and -2 balance out. So again, that you can have this neutral compound. Neutral, you've got to get back to that. And that will lead you to be able to write the structural formula. In this case, it was 1 calcium for every 2 fluorines, which becomes calcium fluoride. Now again, this compound is held together by ionic bonds, which are the electrostatic forces that hold ions together. The electrostatic forces that hold ions together. That's what an ionic bond is. And as we have discussed over and over in this unit, nature favors arrangements that minimize potential energy. As I've said, they want to be lazy. They want to have the lowest energy possible, the lowest potential energy. And the way that they like to do this, in ionic crystals, ions minimize their potential energy by combining in a crystal lattice, which is an orderly arrangement. Oh, I can't spell. My eraser here, sorry. Orderly arrangement of oppositely charged ions. An orderly arrangement of oppositely charged ions. Now, though I don't have you taking any notes on this table, oops, sorry, let me turn my pen back on. On this table, you do need to know this. Just put a big no, as in you've got to know it. You need to understand for each type of compound, ionic and covalent, what you would expect. What is the representative unit? Okay, that's the formula unit that we just did. Remember, we just did the calcium, why is it not writing? Calcium fluoride. We know we've got to have 2 fluorines for every calcium. That's a formula unit. Whereas molecules look the same. They're just called of molecule instead. So if you hear someone say molecule, they're insinuating that it's a formula unit, but it is actually covalently bonded. Bond formation. Okay, you should know this. Ionic is the transfer of 1 or more electrons, whereas covalent is sharing. Type of elements, of course, you're going to have metallic and non-metallic coming together, whereas covalent is going to be non-metallic. Physical state. This is one you may not have thought about, but we have talked about it some and we've explored it. Ionic compounds are almost always going to be a solid, whereas covalent compounds, like sugar, gases in the air that we breathe, lots of the carbohydrates and all the things that make up our bodies can be found in solid, liquids, or gases. There's a lot more variety there. And then melting point, we have talked about. Ionic is high, whereas covalent is low, such as sugar. You may want to make a quick note just to jog your memory, and if you'll remember, the salt did not melt. Solubility in water. Ionic compounds are going to be very soluble in water, whereas covalent is going to be all over the place. It's really going to depend on the molecule. And then conductivity in a solution. Ionic compounds stirred up, such as salt water, they're going to be conductive, whereas you've got sugar water is not going to be conductive. And we also explored that. So just make sure that you understand and know these different comparisons and characteristics of the two main types of bonding here. So we're going to finish out our day here with a quick discussion of metallic bonding. Within a metal, we're right here, vacant orbitals in the atom's outer energy levels overlap, allowing valence electrons of the atoms to roam freely throughout. That's that sea of electrons that we talked about earlier, or talked about last week. The valence electrons are delocalized, meaning that they do not belong to any one atom, but move freely about the metal's network of empty atomic orbitals, forming a sea of electrons. They are delocalized. If you can remember that, that will help point you to all of the other characteristics of metallic bonds. So metallic bonding then is the results from the attraction. Between metal atoms, and remember that's 75% or more of the periodic table are metals, the left and the middle, between metal atoms and the surrounding sea of electrons. And reflect again on the fact that metals like to form cations, which are positively charged, which is another reason they would be attracting electrons instead of repulsing them once they become charged. So this freedom of electrons to move about in a network of metal atoms explains the unique properties of metals. You do need to know these properties. They are high electrical and thermal conductivity. High electrical and thermal conductivity. Now we've talked about electrical conductivity, but we haven't talked about the fact that they are also conductive of heat or cold. But if you think about metals, you can think about that. That's why we cook with metals. That's why we use them in different types of insulation and thermoses and a lot of our applications of metals. Number 2, luster. We talked about the fact that metals are shiny, okay, because of the ability of metals to both reflect and absorb different frequencies of light. The third one is malleability, which we talked about in a bell ringer last week. When I bent the spoon, it's the ability of a substance to be hammered or beaten into thin sheets. Atoms in a metal can slide past each other without resistance in the metal, so they don't break or shatter when struck like an ionic crystal would that's locked into that rigid crystal lattice structure. And our last one is related to malleability. It is called ductility. And this is the ability of a substance to be drawn, pulled, or extruded through a small opening to produce a wire, which makes sense as many of our metallic substances, their best usage or their most common usage is in our wiring, in all of our electronics in our homes. So that's all. Make sure that you go back and review. Look at the goals. Be ready for our quiz.